Thank you so much, Professor Ragmari. So today I'm going to talk about the design of durable and functional biosphere interfaces. But mostly I try to restrict myself in super hydrophobic interfaces, which is easy to understand and it's very classic example. Most of the people are familiar with that. So before I directly move on to that, I'd like to use these slides just to show that how over the time this weightability, the concept of weightability evolved. So if you see probably the weightability concept is there even before 18th of century, but the oil documentation start with the Young's equation in 1805, where he talk about, you can predict that what is the contact angle of a given liquid, whether it is a water and oil on a solid interface. And then over the time, people can realize that they have a different kind of complexity in terms of roughness, chemistry, chemical compatibility, many other things. And when you synchronize them or associate them in a proper way, you can get different kind of weightabilities, which is in fact exist in the nature. And you can just understand that chemistry and topography, and you can mimic them, and artificially you can develop, and you can use them for multiple applications. And I'll take this platform to say that what are the things we are currently doing in our laboratory. We're mostly working on three different spatial weightability. One is under the super oleophobicity, superhydrophobicity, and slippery liquid infused porous interface, which is basically inferred from Nafian's feature plan. Now, those interfaces you can strategically use for different kind of potential applications, starting from oil water separation. Suppose you think about a vast open water reservoir and it's contaminated with the crude oils or oily waste. So you can use these bioinspirated interfaces, which can be associated with different kind of spongy porous interface, and you can selectively collect that oil spillage. Not only that, for the industrial applications, suppose you live with some oil contaminated waste, industrial waste, and before you basically throw it out or it comes to the mainstream, the water, you want to separate the oil from water. So you can simply make a membrane where you can associate either under the super oleophobicity or super hydrophobicity, and you just put them strategically at the two side of this open tube, and you can pour this oil water mixture, and you can simultaneously separate and collect them in two different beakers. You don't need any external interventions there. And top of that, you can also use this super hydrophobicity, which is considered as a one of the it has an inherent ability to self-clean the deposited dust and dirt, or even kind of different kind of aqueous spillages, right? So you can develop some kind of functional textile to protect from different kind of relevant aqueous spillage, starting from whatever the aqueous based beverages you can think of. You can really protect yourself from those accidental spillages. Not only that, you can take the commercially available aqueous paint and you can associate this bioinspired property and make those paint instantly water repellent, and it will be slippery. Not even that, if you strategically associate this super hydrophilicity and super hydrophobicity, you can make an interface that can be useful for anti-counterfeiting applications also. And very recently, we started this venture where we can harvest the water. So there are a lot of water crises all over the world, right? So you can develop an interface which can harvest the water from the water mist or even from atmospheric air, depending on which kind of situation you are. And with a little bit of modulations, you can instantly, this is a real-time video, you can see, you put this interface, biosphere interface, and you can harvest the water from the water mist. And not only that, you can take these biosphere interfaces for sustain or trigger drug delivery or even naked eye chemical sensing. So many things can be possible. This is just a glimpse of like what are the things you can do with these biosphere properties. But the major problem is you have to synthesize the interface which should be durable enough to sustain different kind of um, outdoor conditions, right? So at that prospect, this biosphere interface, this particular super hydrophobic interface, uh, face a major difficulties. Now, before I just go and discuss about this durability issue, we really need to know like what is the parameter that decide that gives this super hydrophobicity or extreme water repellency. So, as I said, this lotus leaf is inherently embedded with the super hydrophobicity, extremely repel the water, where the water content angle is found to be above 150 degree, right? So, if you take that leaf and you see under microscope, you will see these micro features, and each of these micro features further decorated with the nano features. So, they have this two-tier topography. It has a micro domains and nano domains, and it later on with the help of this advanced nanolithographic techniques validated that this dual degree of roughness, this hierarchical of this topography is very important to get non-adhesive super hydrophobicity. Once this secret revealed, then there have an n number of approaches, this top-down and bottom-up approaches to synthesize this hierarchical topograph. And once you develop this hierarchical topograph, you optimize this low surface energy coating, which is naturally there in all these living objects, right? So waxy coatings, which gives the essential low surface energy. And once you have this co-optimization, then you get artificial superhydrophobicity. And this is the techniques, this is the fabrication process widely and commonly followed to prepare the artificial superhydrophobicity. And that is the problem. Why it's the problem? Because if you see this designing parameter, there are n number of process to get this hierarchical topograph mostly built out of this hydrophilic building block, and there you are putting a very nano thin layer of hydrophobic coating on top, because this chemistry is also important, right? Now, once you expose this interface for any kind of physical aberrations, you are compromising this chemical optimization, and it loses super hydrophobicity. Not only that, if you also expose to a very drastic physical aberrations, this topography can severely damage, and that also lead to compromise of this property. So over the time, you can see different kind of approaches are introduced, like post-repairable approach, where the concept is you have a damaged interface, then you can rebuild the topography and optimize the chemistry again. So that means you are refabricating the same thing again on a damaged area, which is realistically is not possible all locations, right? Then another approach came, which is self-healing approach, where what they do, you have a porous framework or porous film, and in the bulk, you can load more this low surface energy kind of small molecules, so that once the top interface is damaged, the chemistry is compromised, then under high humid conditions or even elevated temperature, those small molecules which are trapped in the bulk of this coating can diffuse out, and it can give the chemical optimization on top again. But remember, you again need some kind of stimuli. Not only that, these are physically deposited low surface energy molecules. So even if you touch with the finger, it will compromise the coating, right? So another approach came, which is called three-dimensional superhydrophobicity. Even though it's a surface phenomenon, but you develop a coating in such a way that the chemical and the topography, that criteria is all throughout optimized. So that even though the top interface is compromised and underneath interface is exposed, but it keeps continuing to display the superhydrophobicity. But it is a very difficult job to get such kind of porous coating which has this co-optimization of chemistry and topography. This is one of the approach where copolymerization and precipitations of this nanogranular morphology. But those are like the very fragile, and the scalability is a problem. There are another approach, is layer by layer depositions, where you need 600 time dippings. There are another approach which is called candle soot deposition process, where these nanoparticles, which is just deposited on a glass, as you can see here, because of this candle soot deposited here, and then you can use this fluorinated silane, and you get some kind of porous framework, and you go for 600-degree temperature, and then you get this bulk superhydrophobic coating. But those are not really scalable approach. So the question is how to solve this durability and scalability problem. Yes, they have a lot of design, some of the design which can really give you durable coating, but the scalability is a problem. So we thought about this. Let's start with the chemically reactive nanocomplex so that later on we can modulate this topography as well as the chemistry through strategic deposition of this chemically reactive nanocomplex. So we started with this BPI and 5-ACL, and you can carefully see it has an amine group and acrylate which can readily undergo this 1,4 conjugate addition reaction at ambient condition. It doesn't give any kind of side product. So that is a great thing, right? You just mix two reactant and then you get this chemically reactive growing nanocomplex. But believe me, from this first step to second step, it took almost 8 months to standardize this, to find a sweet spot which can give this desired chemically reactive polydisperse nanocomplex, which just keep on growing. And if you allow more time, it can form a gel. And it takes almost 3 hours to form a gel. You can see the continuous growth of this nanocomplex. And at the end, they remain chemically reactive. Even after forming this gel, which can be shapeable, you can give a shape of a bunny and they remain chemically reactive. You modulate with the selected alkyl amine and you can make them superhydrophobic all throughout the coating, but all throughout the material. But our aim was to develop a coating. So what we wanted to do, we want to take this chemically reactive nanocomplex and we want to spray deposit so that we can get a porous chemically reactive coating, and you can associate different kind of chemical modifications, and that's the way you can tailor either non-adhesive or control adhesive superhydrophobicity. But when we started this work, we took this reaction mixture in ethanol. That was our base point, starting point. And once we deposited, as the ethanol is volatile, they evaporated very fast before this gelation really takes place on the surface, right? Gelation takes 3 hours. Ethanol is very volatile. It readily evaporates out, and it gives very much, defected and puffy coating. Even you can't really post modify. Even if you touch with the finger, it'll just come off. So what we realized that you have to expedite this gelation process. How we can do that? There are probably very much different other approach, some kind of catalysis and all, but we don't want that. We want to keep the system very simple. So we know this dissolution energy some point promote this kind of reactions, right? So we took we changed the reaction media from methanol to pentanol. The solubility of these reactants in this solvents, when you go from methanol to pentanol, it changes, and that help for faster gelations, and that really help us to get a uniform and thick polymeric coating, which remain chemically reactive all throughout the coating. So the coating is almost like 500 micrometer thick, and you can selectively or precisely take out some of the top portion of the coating. And if you see carefully, this is a different depth. This is a different depth that you got through physical aberrations of these coatings. And we've characterized that is irrespective of the depth of the coating, they remain chemically reactive because of these residual acrylate groups. And when you modify further with selected alkyl amine, you can make them superhydrophobic. Whether in the top or the underneath the interior, it all give the superhydrophobicity, display extreme water repellency. Not only that, such platform basically give us to check to examine the kind of role of this precise role of this chemistry. You can gradually change this hydrocarbon chain length, and you can see the impact in terms of this fraction of contact area between the beaded water and the solid interface, the bioinsular interface. And that you can simply modulate just by tailoring this carbon tail length. And that's the way you can modulate different kind of adhesive and non-adhesive superhydrophobicity. And our aim was to get this durable coating. You can see it can survive different kind of standard physical aberrations, starting from adhesive tape peeling test, scratching test, and sandpaper aberration. All this process give different kind of fracture to these coatings, and it exposes the interior differently, right? Irrespective of that, all these cases, it keep continuing to display the superhydrophobicity. It doesn't require any kind of external interventions. Also, the chemical durability remain really unparalleled. It survived acidic river seawater, which is highly saline, right, conditions. So it can survive almost more than a month exposures, prolonged exposures to the UV also. So very quickly, I'll just give the another flavor here. I just keep this work. So very recently, we have also introduced a single-step fabrication process which can give optically transparent superhydrophobic coating, and it can survive, different kind of physical aberrations. This is kind of knife test you can see. Also, this is sandpaper aberrations you can see, where on the you have abrasive rough surface, you're putting the load, and you are avoiding this interface, which is super hydrophobic, right? Even the kind of the the base material, the substrate is fractured, but still the coating can give this extreme water repellency. So that is the great thing here, and you can achieve that in a single step. And these formulations came from just the reaction mixture of small molecules. And in situ, you can choose this appropriate reaction mixture and can modulate different kind of adhesive and non-adhesive wettabilities. Now, just very quickly, I'll give you another aspect of our research where we want to develop a functional resistable superhydrophobicity. When you talk about the superhydrophobicity, always people conventionally put the top layer is chemically inert, right? Either hydrophobic gel or the fluorinated molecules, right? They are chemically inert. Now, is it possible to get chemically reactive superhydrophobicity or dynamic superhydrophobicity? As you can see here, you have we started with a porous poly coating, which have a two different kind of distinct residual functionalities, and selectively you can modify either through 1,4 conjugate addition reaction or nucleophilic substitution reactions, and that's the way you can modulate the residual reactivity, as well as you can embed different kind of water wettability, and that can be used for different kind of applications. So as we don't have much time here, I have to stop here. So but just very briefly, we very recently we have also solved another problem. Like, this Nepenthes feature plant inspired to design this slippery coating, where people generally make the coating highly hydrophobic and then they infuse the lubricant to get the chemical compatibility and then become slippery to the aqueous phase. Very recently, we have proved that this chemically reactive coating allow us to prove that this interface not necessarily need to be highly hydrophobic. Even the coating with this hydrophobic anchoring group, but overall it remains hydrophilic, that can also give this the slippery interfaces. And that has a lot to do. And based on that, you can develop a slippery interface which can harvest the water, with a very high efficiency, almost like 4.4 gram per centimeter square per hour. It can produce the water from the mist. And some of this technology we're working with the industry to for realistic applications. And with that, I'll conclude my talk here. Before that, I really want to acknowledge my students who are the instrumental for this work, and all my collaborators and funding agencies, and my department, Center for Nanotechnology, CIF, and definitely Indian Academy of Science for giving me this opportunity to present some of our work here. Thank you so much.
There is one question, Dr. Manna, from Sarit Agasti. First, he says it's a nice talk. And the question is, how the coatings get attached to different surfaces? What is the chemistry there?
So this is a great thing. So here, basically, what we are doing, we are starting with the reaction mixture, which remain in a polymeric form, right? And now they are in situ depositing and forming the gel on the surface. So that's the reason we found that it doesn't really matter whether you are taking the glass or the wood or even the paper. Irrespective of that, it can give a very strong adhesions. So because of this lack of time, I couldn't really show that experimental validations that is there. Now, why it is, right? So all of these interfaces, they are with, so if I think about the metal top is basically somehow it has always some oxide layer, right? So some kind of this ionic or hydrogen bonding interactions is there. On top of that, you have this in situ deposition of this gel, which is inherently sticky to these interfaces.
Okay, thanks, Uttam. There is another question from Professor Bhaskaran. The comment is, water is special. It has hydrogen bonded network structure. Is there a role of network properties or its flexibility in determining wettability?
Yeah, so as you mentioned that, the flexibility, right? So even these interfaces, I can take examples where, superhydrophobic interfaces can be used to even prevent the ice formation. So it found that you can put the water droplet and you expose that whole setup in a very cold temperature, even below minus 15 degrees centigrade temperature, and it can form the water droplet frozen, but they remain with that very high water contact angle. So this hydrogen bonded network around this water probably has an impact, but that impact is not that severe.
I have one quick question, Dr. Manna.
Sure.
Your work on chemically reactive hydrophobic surfaces was quite interesting. It seems chemically sort of conflicting requirement that somebody surface should be active as well as hydrophobic. So
Right.
the entities with which it can react, do they also have to be hydrophobic, or is there any, what type of entities will it be reactive towards?
Right. So, if I just talk about the superhydrophobicity, the superhydrophobicity arises because of this metastable trap here. It's a metastable, it's not permanently stable. So, at a given situation, it can be displaced, and then you get the liberty to modify the interface with any given kind of molecules from even from the aqueous phase or from the organic phase, whatever the things you can think about. So, that displacement of trapped air that can be easily possible to do with even ethanol or methanol, which are low surface tension solvent, right? Even you can take the very highly elevated temperature, like kind of above 80 degrees centigrade temperature. At that point, the trapped air will displace, and you see the interface will be kind of, no more super hydrophobic, no more resistance towards the aqueous phase.
Okay. We have another question from Professor T.P. Radhakrishnan. How problematic is the pinhole formation in the coatings on the substrate due to possible de-wetting issues of the coating itself? If I understood it correctly, the substrates are not always functionalized.
What our strategy is that, yes, so what kind of chemistry, what kind of applications we want, right? So some point we can come up with the two different kind of residual reactivity. So where one kind of residual reactivity allow me to satisfy that chemical criteria, that low surface energy, right? Another functionality is kind of remain hidden there, and is buried behind these long tail hydrocarbons, right? And when I want to modify the interface, then I can displace this metastable trapped here, and the small molecule can find the way to reach the another residual reactive group, and you can modulate that, and you can modulate to achieve different kind of functionalities in these coatings. And in one of the slides, I also show that you can tailor even this contact area, fraction of contact area between water and the substrate through this precise chemical modifications.
All right. If there are no other questions, I think we are done with most of them. Just a second.
Thank you. Thank you so much.